It's a great honor to speak at this series in this venue, so thank you so much for coming. I'll speak about, well, in fact, integrability in general, but focusing on one particular example, the Sine-Gordon model, the duality with the Thirring model. These are two-dimensional models. But the purpose will be to actually give an idea of why integrable systems are nice, why they're useful, and why they have such a big impact in theoretical physics today. So let me give, as a beginning, an outline of all the lectures, so you have a sort of map of what I'll try to do with the timing. I haven't rehearsed this, so I'll completely change the schedule. So day one, which is a little intro, 10 minutes. Then we'll speak about classical integrability for another 10 minutes. Then we'll do quantum integrability. This is to set the scene for the core of the topics of the lectures, which will come later in 2 and 30 minutes. Then maybe 5 minutes break. Schedule. And then we'll spend the rest of the day to describe classical Sine-Gordon as a particular example of an integrability, one of the most famous, in fact. 40 minutes, and then maybe some comments on exercises. I hope you can have access to the notes. Maybe that we put on the website, but I'll try to put together a set of notes and with exercises. No solutions, but again, have a go. It's completely non-examinable if you wish. But feel free to drop me an email, try. So, day 2, next Monday, then we'll describe quantum Sine-Gordon. This will be some facts, because the theory is so complicated still, though integrable, that I'll just collect some facts that I've studied myself and tried to learn. It's hard to develop any kind of real expertise. The field is so vast, so I also do a little fraction of it, and I have to learn a bit of these facts, which have been developed with the decades. Then we do the S-matrix, the exact S-matrix of Sine-Gordon. 30 minutes break. Then we describe the relationship of Sine-Gordon to a spin chain, XXZ spin chain. And this will take us into the theory of quantum groups. Quantum groups are the mathematical language to formalize theoretical ideas behind integrable systems. In particular, this would be the SU2 Q-deformed quantum group. And then comments. This would be some sort of 40 comments. And then day 3 will be the actual duality. So I'll talk about the Thirring model, which is a model of fermions, while the Sine-Gordon model is a model of bosons, at least nominally. But they're equivalent, so you'll soon discover that they describe the same physics. The statement of the equivalence, which is something which was worked out by Coleman. Then we describe something called form factors, because they will give us a way to test the equivalence. This will be a statement, and then we need to prove it, and that will be via form factors. One test, there's many tests, but the ones I've focused on. So we'll do form factor axioms for break. Then we do Sine-Gordon form factors. So this will be in general, every integrable model is amenable to some axiomatic treatment of form factors, but then we'll look at the solution of the axiom for Sine-Gordon. Sine-Gordon form factors. These times basically don't mean anything, just mean to give a sketch. We'll go completely over time. Test the determinants. And find. So this, along the way, should reveal some of the power of integrability and the beauty that is hidden. Okay, so this basically is the introduction. So let me start with classical integrability. So the point of studying integrable systems, both classical and quantum mechanical, is that in general quantum field theory, and so classical field theory, is very complicated and it's difficult to find exact solutions. Basically, as soon as you start putting some interactions, fields, then you lose pretty much the privilege of having exact solutions to the equation or the correlation equation. So the beginning could be stated as quantum, but in general, field theory itself is complicated. And so we need some kind of toy model to train our intuition, because perturbation theory is fantastic, but there are certain things that happen at the non-perturbative level which we would like to have control. So we need some toy model. And there are various examples, topological field theories, conformal field theories, all have one feature in common: symmetry. You have so much symmetry, the system is so constrained that you can actually solve the equations exactly. Integrable systems are one such example. Integrable systems, integrable field theories, can be solved, at least in principle. I need to put a disclaimer. As usual, you find out that when you start doing integrability, the equations that you end up with are so complicated that more often than not, you cannot actually solve them. You need to resort to numerics. But you can go surprisingly far, certainly much further than on an ordinary field theory, which is completely wrong. And this is again because of the huge amount of symmetry constrain the problem, and it's well known that they allow you to go much further. So how do we see in an integrable field at the classical level the emergence of such symmetry? Well, there's a notion which is quite important, which is the notion of black sphere. So, for all practical purposes, the classical field is thus integral if and only if the equations of motion are completely equivalent to the following system. Which we write like this. dt minus dxm equal n, where L and n are matrices of some dimension, and they depend on this value, on this.
Only for 2D?
2D, yes, yes. So I'll quickly show that this. So yes, I need to make a remark. So that's a good point. Without, it's so natural to just, I basically live in 2 dimensions, so I didn't even think about it. But all we're going to be saying is in 2 dimensions. So these field theories live in, let me say, 1 plus 1 dimension, because I will be, for most part of the lectures, dealing with relativistic theories, so relativistic invariance will be. But of course you can generalize, and there's people in the room who have done a lot on string theory, integral sin theory, for great relativistic environments. But for the purposes that I'm interested in, we'll do 1 plus 1 dimension, and there is, I'll mention it later when we come to the quantum part. There are various theorems that justify, in fact, that force you to be in 1 plus 1 dimension. It's very difficult to conceive integrable systems in higher dimension. Not to say that they don't exist, but they have to be concocted in a very special way. So the majority of systems we're dealing with, and you'll be dealing with if you study integrable systems, is 1 plus 1 dimension. So if you have a field theory, 1 plus 1 dimension, and the equations of motion are completely equivalent to this system, then you call it integrable. L and M are called a Lax pair. It's a pair of matrices. They depend on the fields, of course, the fields of the theory, and also they depend on an additional variable, a complex variable. We call it U, which is typically referred to as the spectral parameter. The spectral parameter is very important. It doesn't have any immediate correspondence in the physics. It's an additional parameter, so I will never write explicitly, but every time L and M, they also depend. So how can I prove that this immediately gives me some conservation law? The amount of symmetry. In fact, an infinite power. I'll do this little exercise to show that if I have reached this point, then I can immediately construct these conserved charges. So let me erase everything again. I need to define an object which is called the monodromy matrix. And you see, now I've lost the details of the theory. I can proceed purely mathematically from this equation and study it. So once, for the practitioners, this is actually a difficult task, because there's no, to my knowledge, systematic procedure, even a set of equations of motion, to find L and M. In fact, well, if they exist at all, it's not clear. In textbooks, you'll find various sort of constructive approaches, but they're not absolutely clear-cut. It's a bit of an art to find a Lax pair. Even if you know by other means that the theory has a chance of being integrable, it's a great success if you can actually manage to find the Lax pair. But once you have it, this comes for free.
Sorry, can I?
Yes, of course.
Like, is this statement that if a theory is integrable, then Lex pair where it exists? Is it like the definition, or we just don't know other examples of integrability?
So that's an excellent question. In finite dimension mechanical system, there's a clear definition of integrability, Liouville integrability. It means that if the system is on a phase space which is 2n dimensional, you just need to find n conserved charges which are in involution, they commute. That's a clear enough statement. One can take it as a definition of integrability of the mechanical system. In field theory, the degrees of freedom of the phase space is technically infinite, so it starts becoming murkier. It's unclear what one means by integrability. So one very pragmatic approach is I take this as a definition. I define a field theory integrable if and only if I can write the equation of motion as an answer. It's a sort of minimalistic approach because it's a constructive approach. I can show that from here I get the conserved charges. There is an extra step which is proving that the conserved charges are in evolution, but that I will leave aside for this lecture. There's a whole subject in mathematics which is the theory of R matrices and Skrianin brackets, Maillet bracket. They will tell you whether you get Liouville integrability, so that the conserved charges are also Poisson commuting among themselves. That's another step. If you want to read more, there are some lectures which years ago with other colleagues I wrote stemming from some courses we gave in Durham. So in the notes there's references. So there I say much more about this classical Poisson bracket and classical integrability of mechanical system versus field. So
Okay, yeah, thank you.
Okay, so let's define the monotone matrix. Monotone matrix is constructed using the matrix L. Let me call it T. It's not sometimes T is reserved for the trace, but I think I had another lesson for N. This is the path order exponential of the integral of L dx, x and t. Let me just say it once and for all. I have a signature which is minus on the time. That's my convention. And I'll put some extreme. So I'm on a line now, 1 plus 1 dimension. So let me define, in fact, an object for shorthand notation, TAB is the path order exponential on some interval. So this object is the monodromy matrix, and I want to show that if I take the trace, so the trace is called, so it's also got a name, it's called the transfer matrix. Is conserved. So for this, I'll do this little proof, which is instructive, because it just uses very simple. So the path order exponential, the direction will be chosen so that what I write now makes sense. So let's compute the derivative with respect to tau, t time, of TA. So this, because of the path ordering, now will be integral a naught dx. Then there is a t, so a dx. Here the ordering matters because you can see how I split the integral. Then there is dt of L, implicitly this point x. And then the rest of the path order, t a x. Now you see that I can use the Lux equation. So we write it here. L minus xn was equal to na. So I substitute this x dxb. The whole thing will be dxm. I write it as minus m changing the commutator dx. Now this is actually a total derivative because I can write it like this: integral dx of tx m, the position x, so this is the position x, tax. You can see that if you differentiate these guys, once L comes with a minus, comes down with a minus, and once it comes down with a plus. So it's the integral of the total derivative. It just goes on the extrema. So this is just m of b. So in b, this is 1. The integral will be between b and b. M of b, t, a, b. Minus t, a, b, m of a. At this point, I have to make some assumption. I could decide that my theory lives on a circle with periodic boundary condition. I could do many things. I could say that this is minus infinity, this is plus infinity, and the fields decay sufficiently fast so that the whole thing is 0, because M will be made out of the fields. Or I could do something a bit more sophisticated. Let me go on a circle with periodic boundary condition. This means that M of A is M of B, because all the fields are in M, the periodic. And so this is the commutator of the unique value M of A with 1. Therefore, now it calls to be taken trace of, because I have a time derivative of something equal a commutator. If I take a trace, I get 0, trace of the commutator. So this implies that dt of trace of TA is trace of the commutator. So I've proven that it is conserved. You might say, well, you found one conserved charge. It doesn't seem striking. But here is the point where the spectral parameter comes to play. So let me erase the top and make a comment that the importance of the spectral parameter is that now I'm going to write it. So actually what I mean is dt of trace of TAB of u is 0, because everywhere in the fields there is, everywhere in the Lux pair there is u, the spectral parameter, on top of the field. And so
Which
I
is
have
completely mysterious, and God knows why it's there, right?
Exactly.
Field, like, where did it come from?
Yes. Indeed, it's sort of, in a sense, it's here the power of analyticity comes in magically. Because now I have a functional equation. So this is a functional equation. And depending on the problem, I can decide to expand, say, in Taylor series, or Laurent, or any other series of functions of U, trigonometric, Fourier. The point is that I will get infinitely many coefficients in principle. Of course, you could have general cases, but the last one is trivial. There are such pathological integrable systems, but in general, you get an infinite series of coefficients. They only depend on the fields, and they're all conserved. So that's depending on the fields. In a sense, the transfer matrix is the generating functional of the conserved changes. You get them all by expanding in the series or some other series. So you've done what we were discussing before, half of the job. You have an infinite tower principle of conserved quantities. Whether or not they Poisson commute is for another day. It's the theory of R matrices, classical R matrices. Okay, any question on this which ends classical? Yes.
So, is there any requirement for these series to converge?
I think at this point I'm gonna call in the physical principle of we write down expressions and then we look at them and we cross our fingers if they converge, okay. If they don't, we try and figure out why. But yeah, from the point of view of functional analysis, probably I would put a lot of assumptions on the Lux pair in order for this to converge. But in practice, case by case, one goes and sees the example. Okay. It's an excellent point. And I think the theory of classical integrability goes very quickly into very complicated functional analysis. There's something called Gelfand-Levitin-Marchenko equation, which actually controls solutions of integral equations. So it quickly becomes analysis.
Sorry, I have a question.
Yes.
It might be stupid, but I found this TAB is very similar to the form of a Wilson line. So I'm wondering if there is any relationship.
Yes, basically it is a sort of one-dimensional version of the Wilson line. This Lux pair, it sort of is the language of gauge theory, although it's now reduced to a sort of two-dimensional. But yeah, the language is the same. In fact, I think the proof of conservation can be made much more geometrical. This was kind of brute force, taking time derivative, but knowing the Lux equation, you could actually make a geometrical argument based on curvature, but this had to be conserved. So yes, absolutely, that would be the right language.
I suppose Kevin would say that the right gauge theory is four-dimensional Chern-Simons.
Yeah, it's very interesting that there's a history, in fact, of master equations for integrable systems. I was reading somewhere that self-dual Young-Bills in 4 dimensions is also supposed to be a sort of mother of all integrable systems. By reduction, you obtain this. Also, the KP equation is another one, in 2 + 1 dimension. So you could lift this, and then, according to various projections, you could get a lot of known integrable systems. Okay, let's now quantize this. So, now once you've discovered that the classical theory is integrable, there is a good chance that a lot of the structure might be preserved by quantization, but of course, as you know, quantization is quite a violent leap you have to take. So you might break things by regularizing, you might have anomalies. So we'll just assume that we are dealing with good system, which means I will assume the quantization that I can find. A quantization which preserves integrability. So all these charges will still be conserved. They will commute with the quantum Hamiltonian. They commute among themselves in evolution. It's up to me to find such an example. Sine-Gordon and Thirring are not the simplest way to see it. They're a very rich system, but there's even more toy model types. For instance, the nonlinear Schrödinger equation. That is one of my favorite examples because you can see that this happens using normal ordering of operators. So you literally sit down, quantize a normal order, and you get preserved quantities. So, but of course, the nonlinear Schrödinger equation is more reductive. It's in a sense, less rich system. But for the purposes of this lecture, we'll assume that you can find a quantization scheme that preserves integrability. What kind of consequences does this have on the dynamics? If you have so many conservation laws, I haven't said that at the classical level you have a lot of consequences. You can find exact solutions, and we'll see in the case of Sine-Gordon, you have solid solutions with certain features. Quantum mechanically, you also get a counterpart, so somehow I've made a logical turnaround, because I'll first describe the consequences at the quantum level, and then we'll do next time, or no, next hour, we'll do classical Sine-Gordon and see the solid solutions, which is sort of classical. So the consequences.
Sorry, this quantization that preserves integrability is believed to exist for every integrable theory?
No. It has to be shown, and it's usually a lot of pain and sorrow.
So this restricts the class of the theories that we're looking at?
Yes. For I would say that all the models that appear in the literature are survivors. Are those models such that this has been found by some mathematicians and physicists came up with the right quantization? But yeah, it so happens that classical integrability is a very big stepping stone. So on the top of my head, I don't really know of a model which is classical integrable whose quantization was never found. But this might just be me not knowing enough. Or perhaps those are not survivors, so they're forgotten by this. So, what is the consequence on the dynamics? Well, in quantum field theory, we talk about scattering. So all of a sudden we have particle accelerations. I'll show in the case of Sine-Gordon an explicit example, but at the moment you see I'm making quite a lot of assumptions. I'm saying that these particles are in the spectrum. So I'm not talking about perturbation theory. I'm talking about the quantum spectrum of the full Hamiltonian. It's then up to me to have to demonstrate it. So there'll be particles, and they will particles. This scattering is highly constrained. So, integrability puts a lot of constraints on scattering of particles, which is ultimately one of the observables, one of the chief observables we want in quantum physics. Let me just list the number of restrictions. And in the end, we'll see that they form an axiomatic structure which is perfect to then be promoted to a mathematical framework. They become, all these constraints, they become axioms of scattering theory, what I will call the integrable scattering. So first of all, there is no particle production or annihilation. This is in the full amplitude. So I will always talk about the full amplitude, not the individual final graph. That, of course, will be full of production and annihilation because there's vertices in my theory. But once you sum the whole perturbation field, or if you wish, if you compute the full block, which is the scattering amplitude, there is no production, neither annihilation. The particle number is conserved. The initial and final sets of momenta are equal, which means not only the momenta are conserved in numbers, because the number of particles is conserved, but they're the same. They just swapped and reshuffled, permuted. But it's the same set. And then there is something called factorization, which means that any end-to-end body scattering factorizes into subsequent products of 2 to 2. In a sense, these particles are on a line, and like on a billiard, they scatter pairwise, and that is how they resolve the full scattering. In ordinary QFT, this will not be the case. You have an n by n amplitude, and you just have it. Here, you can always factorize. This is an extremely powerful relation. This happens because of all these conservation laws. There are theorems that have been developed based on the conservation of these quantities that show that this is the only thing that actually can happen without violating those conservation laws.
Can you turn it the other way around? So if you wanted a theory with no production or annihilation, does that then mean you have to have all these conservation laws?
I would say tentatively yes, although I'm always cautious to do the other implication because you could have theories that just happen not to have. I think there is an example. There was a model studied, I believe, in the 70s called the Lee model for particle physics. That was concocted to solve renormalization group equations exactly. So they had in mind, can we find a toy model for renormalization? It was constructed so that, because of some conservation again, only two particles could only go into a specific third particle, so that an entire set of diagrams would be killed entirely. I don't think that theory is integrable, but is designed so that effectively you have, well, maybe not factorization, but you have conservation of momenta. And so I'm not sure there's an exact equivalence. All the models that are really used nowadays, they satisfy this. It is certainly true that you need to have some symmetry. That model had a particular conservation, some transition which was depressed by superselection rule. There's always need to be some symmetry. Right.
Sorry, just a quick question.
Yes.
It's like maybe fairly silly, but how do I think about this for odd n?
In fact, 3. Let's do 3.
Yeah.
So, time 1, 2, 3. So S, S. What I would call S 1, 2, 3, the whole block, which I would write like this, is actually S12, S13, S23. So there's some sort of permutation group mathematics behind this.
Sorry, do we have multiple types of particles here, or is it all the same kind of?
It has been schematic. You could have different particles, each with their own 2 by 2. So all it's important is that I know the type 1 and 2, when they scatter, I have a particular S, and with 3 another S. So these could be different functions, but depending on the scattering pattern.
So does this effectively mean that if you have two particles of the same type, they effectively pass through each other?
But the spin or any other degrees of freedom could change. That's indeed excellent point. I need to make this remark. So this doesn't mean that the theory, in a sense, reduces to a function. In fact, such scattering can still be very complicated. It's infinitely simpler than any generic UFT, but it still be complicated because of the degrees of freedom. So I only conserve the momenta, the kinematics, but the spin, flavor, superalgebra representations, I can put in polarizations, they will transform. So S effectively will be a matrix in the representation, in fact, in the tensor problem, of some superalgebra, if you affirm it, with entries depending on momenta. Now they do depend, so that each entry is a function of the two scattering momenta. This S1, 2. But the matrix could be as big as you want depending on your polarization. If you have an infinite dimensional representation, which problem 9 we've met in our research, you have an infinite by infinite matrix. So it's still a problem. How do I find it? Because now I'm curious. Now there's so much symmetry. Now I want to see this matrix. And we'll see the Sine-Gordon. Are there any other properties that this S12 has to satisfy? Yes, there's a list. I'm going to give you a list of axioms which come from field theory plus integrability. So now I'm going to focus on S12 as a matrix valued function of the momenta. And what are the axioms that I need to satisfy? So, first of all, I am in a relativistic theory, so in a relativistic I can parameterize my particles, that is pi, the momenta is. Let me choose equal mass. Again, this doesn't have to be, but for simplicity, I could have all different masses. But let me just, for simplicity, use equal mass of P1 and P2. So I use the rapidity, the I, and the energy satisfies the relativistic dispersion. This is the rapidity. It is additive under the only Lorentz generator in 1+1 dimension, which is the boost, which adds a constant to the rapidity. So if I have relativistic invariance, or boost invariance, it means that the S-matrix, which you see, dependence on the momenta would be that it depends on theta 1 and theta 2, is actually a function of the difference. So it's a function of only one variable theta, by which I call the difference. Theta 1. So further simplification, I have a matrix valued function of one complex value. Why complex? Of course, momenta on the shell are real, but it always pays off to continue analytically. So we used the philosophy, which was popular in the 60s and 70s, of the analytic S-matrix. You have S-matrix amplitudes, you have correlators.
So, where's the spectral parameter?
Here it is not present because we are on shell. So in some sense, I'm just computing the scattering.
That's fine.
So the philosophy that goes through this is the philosophy of the S-matrix program, whereby you can extract a lot of information from quantum field theory if you look at the analytic properties of correlators and S-matrices in the complex plane of momentum. Here it would mean in the complex plane of the difference. So this will be the plane where I will be making my analyticity consideration.
Or did you say that theta is the actual parameter? Spectral parameter?
No. In this case, theta is the actual physical rapidity. These are really the physical rapidities of my scattering particle. And the difference, so they're real. If I have to solve the scattering problem and find the cross section, they will be real. But it pays off. It's a sort of, again, unspoken philosophy, rule of thumb. It always pays off to look at the amplitude and extend it analytically to the complex plane and use the power of analysis. Of course, the physical cross-section will always be found by reducing to theta real. In 1 + 1 dimension, the cross-section is a bit trivial because you're in a line, so everything will hit the target. There's no phase angle, there's no Fermi golden rule of quantum field. But still, you have an S-matrix. It basically controls the wave function of the scattering. So let's write in the last bits of the first hour, let's write the list of axioms of scattering, and then we'll take a little break. So the first axiom is what we call braiding unitarity. It's not the unitarity of scattering, that is physical unitarity. I'll write that later. This is basically this diagram. So this is S12. Let me write theta as if it were an angle, although it's a kind of hyperbolic angle, but it's a difference of angles in some sense. So S12, this is how I write S. Braiding unitarity is this. If you do the scattering and then undo it, it's like doing nothing. And of course, if I have to write in formula, schematically, is this. S12 of theta, S21 of minus theta is the identity. Why this? Because if this is theta, here they scatter at 2 pi I minus theta, which is minus theta. This is a sort of 2 pi I periodicity. And then I need to exchange 2 and 1. So I'm putting the polarization of particle 1 and 2 here. It's schematic because we will find later on, we will encounter a sort of formal way of writing it using quantum groups that doesn't make use of any shorthand notation. It's a fully mathematical principle. This is a bit of shorthand. Braiding unitarity. This is something that has to do with integrability. Then we have crossing symmetry.
Sorry, so is this an axiom you're putting in, or is this a consequence of integrability?
So at this point, it's not directly a consequence of integrability. It so happens that every integrable system, well, in fact, not every, most of them satisfy this. So what comes after this is a strange list of axioms. It's not automatic that all of them have to satisfy. The logic would be the more the better. The more you can satisfy, the more you can constrain the S-matrix. Typically, integrability descends from quantum group, and there is a relation in quantum groups that basically descends to this, and so this would be derived from the universal R matrix of some quantum, which you will see for Sine-Gordon is the case. But again, these are not strict axioms for every integral system. They're also relativistic, so they'll be analogous for spin chains and cases where you don't have difference form. You need to relax some of this notation.
Whereas the constraints that we talked about before,
those happen all the time. For factorization, that's sort of a hallmark. Again, modulo some very pathological mathematical examples which might not have any physical. So I think you're seeing that I'm struggling because it's hard to make this into a rigorous mathematical without reducing to very simple systems which are almost trivial. So there's a bit of mix between mathematical axioms and reasonableness of the physical systems. One might always find a counterexample which is some very pathological theory somewhere. Let me write all to reassure us, Sine-Gordon will satisfy all this. So if we are uncomfortable with this, we could think that I'm just describing all the properties of the Sine-Gordon S-matrix. This will always be guaranteed. There is something called crossing symmetry that again descends from local theory. Crossing symmetry is basically this diagram. I can read the scattering in the S channel or on the T channel. And the two things have to be the same. So between 2 and 1 is the same. If I look through here in time, I could also look at with time through here, and then I will have this. So in formula, S12 at an angle theta is S2 bar 1 at alpha. Again, schematically. These are matrices, so I'll have to multiply them. Technically, I should also put some charge conjugation matrices, because now I've transformed. You see, the particle that was in the future now is in the past, so I've done some charge conjugation. There will be a quantum group formula that encapsulates all that. But schematically, it's the equality of these two diagrams. That just comes from local. Then there is the Yang-Baxter equation. This is typical of integrability. In some cases, again, if one wants to make an axiomatic approach, one could just define this as what it means for a system to be quantum integrable. That the S-matrix factorizes and satisfies the Yang-Baxter equation. The Baxter equation has a history in mathematics. Star triangle equation. It's many names. It's this. Now I need to make explicit all the differences. Again, this is now a matrix equation on the triple tensor product of three particles. Schematically, it's the equality of these two diagrams. Right? One, two, three. They meet in different order. This statement is what makes factorization meaningful, because when I said that the scattering factorizes into a product, you could have argued that you could do it in different ways. In fact, you could do it in two ways. And this is the consistency that says that it doesn't matter which way you factorize, whether these go first, or these. It's the same. So there's only one way really to factorize this scattering. The final thing I'd like to mention is the bootstrap. Well, I see that it's getting quite late, so let me just say the bootstrap and then we'll take a break. The rest of the considerations are in the notes. But the bootstrap is a lot of fun. Let's do the bootstrap for last. Bootstrap. Bootstrap is a name which is very popular on the archive these days. This kind of bootstrap is a bit different. It's not a conformal bootstrap. It's an S-matrix bootstrap. And it says this. S-matrix bootstrap. Suppose particle 1 and 2 can form a bound state. This could happen. Suppose 1 and 2 form a bound state. This, according to standard S-matrix law, would manifest itself as a simple pole in S12. So there is a simple pole in some of the entries of S12 of theta at a particular value of theta which is unphysical, because you know the bound state has to be localized, so it has to have imaginary momentum. So theta will be such that the values of the momenta are unphysical. The pole somewhere. Here you see the power of analyticity. I'm going in the complex plane, in some unphysical region, I find the pole. That reminds me that there's a bound state in the theory, and the S-matrix will become some sort of right figure distribution. Okay, let's call this angle theta. There's some specific theta bar. That's the value of the pole. If this happens, the bound state, if it has the right residue, there's a lot of physical conditions on the residue of the pole, it means that it lives in the theory. It's another particle with another mass, another dispersion relation. So it could conceivably scatter itself with all the previous elementary one. Now, what is elementary and what is composite is a bit a matter of discussion. In this picture, 1 and 2 are elementary. The bound state is composite. It appears in their spectrum. So it could scatter. Let me draw schematically this, which is not a real-time diagram. 1 and 2 form a bound state at theta bar. B lives for long enough to scatter another particle 3. Again, this will never happen in real time because this is imaginary. But I just use it as a bookkeeping device to say that there's an S3B. S3B is the S matrix of 3 with the bound state B if the bound state is put on shell, which is not in this diagram. This is just a picture. Does it mean that I need to compute again another object? No, because this also factorizes. The bookkeeping device just says put the line down parallel to itself 3. 3 is another type as 1 and 2. It's also fundamental. And so I get, now theta is this angle. So 3 and B scattered at angle theta is the same as 3 and 2 at theta plus I something as 3 and 1 theta plus I something else, and this something else you work out from the picture because now they are angled. You forget about the I, you just use the rule of triangles. So I don't need to compute anything new if I already knew the fundamental S-matrix, the elementary one. Let me show you how this works in a very simple model, which is the Lee-Yang model, which is the most beautiful thing, and it's also quite bizarre.
So what is the bootstrap? What exactly?
Bootstrap in the sense that I don't need to do anything else, I just use all the information.
Right, okay.
It seems to have this sort of meaning, an ontological meaning of using old stuff and put it up. So let me show the most bizarre of all examples I've ever found of bootstrap. The Lee-Yang model, where the particle is a bound state of itself. So Lee-Yang model example. So the particle appears as a bound state of 2 copies of itself. 2 copies of itself. So B is the same type as 1 and 2. So the formula looks like this. So first let me give you the S-matrix. Here there's no spin, there's no polarization, there's scalars. So the S-matrix is really a function. We finally see one of them. S Lee-Yang is sinh theta plus I sine pi over 3 sinh theta minus I sine pi over 3. Incidentally, you see it's a unitary object, it's a phase, physical unitarity. It satisfies minus theta, S of minus theta, S of theta is 1. It satisfies all the axioms. You can check crossing symmetry. What is the bound state pole? Theta is 2I pi over 3. Simple pole. Bound state. So I can write a bootstrap, and it looks like this. And you can check it with one line of calculation, which is now elementary function. And you can draw it here. Basically, this is 2I pi over 3. You pull this line down. So this you pull down. This is I pi over 3. This is also I pi over 3. This is theta, because this is a vertical, not exactly, but it's meant to be a vertical. This is parallel. You fill the triangles and you get this nice exercise. This is the bootstrap, and this function satisfies this quite magically. The only disappointing thing I'll leave you with in the first hour, and this is another exercise with a reference to a paper of Penedones and Vieira, which is in the notes. If you compute the residue, it has the wrong sign. So residue is the wrong sign. I haven't said what the sign should be, but Penedones, Vieira et al. Explain it in the review. This has the wrong sign. Famously, the Li-Yang model is not a unitary. But it's integrable and satisfies this. Okay, let's take a 5-minute break. That's all right. So let's discuss the Sine-Gordon. Now we've seen sort of basic, as axiomatic as we could go. Now we delve into the specifics of the Sine-Gordon. And today we just look at the classical. So, to start with, let me begin with a simpler view and try to motivate how Sine-Gordon could actually be constructed if I require integrability. So let's first consider phi to the 4. And this is an argument, again, the notes we thought we made available. There's a review by Patrick Dorr called Exact S-matrices. It's referred to notes, so you find all the references. So this example comes from those notes. So consider phi to the 4 in 1 plus 1. So in my notation, phi, massive 1, phi squared, lambda, Torrielli, phi. So let's consider this, which is a very familiar note. And let's try and complete. This is obviously non-integrable, but obviously, if you start computing, you see that it doesn't really satisfy the axioms. What can I do to make it integrable? Well, for instance, I can compute perturbability a certain amplitude, which is 2 going into 4. This would violate, at least perturbability, integrability. It might still be that, you see, I was always talking about full amplitude, so by some magic rearrangement it could still be the full amplitude actually vanishes. But if it starts being non-zero at the pre-level, probably. So if you compute it, I will not do the calculation, of course. Now I will have to start using known facts from the literature and put them out from the papers. It turns out to be a constant, and it's so it's a constant. Sorry, particular constant. And being it a constant, I can simply cancel it with a phi to the 6th term. I can just put a term, can be cancelled. Adding to the Lagrangian the following term, minus lambda squared over 6 factorial m squared phi 6 to the Lagrangian of sine. Well, the Lagrangian of phi. You already start seeing where I'm going. So I found that there is a non-trivial amplitude which breaks integrability because this is creation and annihilation of particles. But I have the freedom to change the theory by adding a term which cancels it. But this now generates a 2 to the 6th. So this generates a 2 into 6 trillion diagram, which is also constant, and I won't write it, but in the review of Patrick Dorr you can find. So can be cancelled. By a certain phi to the 8 term. But this generates 2 to 8 and so forth. So you discover that if you want to cancel them all these unwanted creation, this would be creation, not annihilation, but if I do time reverse, it would be annihilation. Well, to cancel them, I need to add a lot of terms, and these terms make a series. So to cancel them all, the unwanted creation amplitudes, 3 levels, of course, that's all I'm doing at the moment. Amplitudes. I have to add infinitely many terms, but they're not, you see, they're nice, because I know the coefficients, and if you work them out patiently, they start making a known series, which is the series of the Cauchy. So the series just sum up very nicely, and it's minus m squared over beta squared, I'll tell you what beta is, Cauchy beta phi minus 1, where beta squared, the whole thing is even in beta, is lambda over m squared. This is quite a remarkable fact. Let's make some comments. So, first of all, I cannot be content about trivial, because of course that would be very reductive, but I trust the holy textbooks that tell me that this can be worked out at loop level. I will not do it, but the first comment can be extended to some loop level. Of course, it starts becoming complicated. But this allows me to make a remark which is very common for practitioners in integrability. Once you start noticing that something has the chance of being integrable, you just guess the answer based on the holy principles and then check. 9 out of 10 times, it's the exact answer. This art, if you wish, it's also an art, has been perfected by the two homologicals to an extreme point. You read these papers where they conjecture exact S-matrices based on very few scattered perturbative data, and they work. They check other things, and it all works out. They never really do the 17 looped, they don't need to, they know that it's true. So you just use other methods, use exact methods. Conjecture and use the axioms. Of course, perturbation theory will always be there to check.
Please continue to circulate the info.
It's been signed by someone. Please can find it.
Did somebody not sign?
So let's make another comment.
Where's the pen?
So the other comment is, you might complain that in a crossing symmetric theory, the 2 to 4, for instance, have been eliminating the 2 to 4. So eliminating the 2 to 4 amplitudes superficially would kill the 3 to 3 by crossing one path. So what about 3 to 3? And 3 to 3, we've learned in the other hour, we would like to keep. We would like to retain this because it's one of the Jan-Baxter things. We don't want to kill the entire scatter. This is very subtle, and again in the review by Dory, it's quoted in the notes, it's just because of the special kinematics and 1 plus 1 dimension, that it is not true any longer that you get the 3 by 3 Feynman graph by crossing one leg of the 2 to 4. So there is a subtlety in the I epsilon. It's quite deep into the Feynman graph technology. But because of this special kinematics, there's some singularity which breaks this superficial expectation. So this is non-zero, that with cancel is zero. The special kinematics, let me write it once and for all, I should have done it in the other hour, can actually easily be written in this way. So 1 plus 1 dimension, it's worthwhile saying that the usual Mandelstam variable. So I have 2, right, 3 and 4. So 1 and 2 incoming. 3 is here, this is P4. P2, P3 outgoing. Then I have P1 equal P3, P2 equal P4, S is S, S is the Mandelstam variable P1 plus P2 squared, the square of the center of mass energy. T is P2 minus P3 or P1 minus P4 squared, it's the T channel amplitude. It turns out to be 4m squared minus s, and u is, because it's P3 minus P1. So effectively I have only one Mandelstam variable, so you see it's quite a degenerate kinematics. And because of that, I do have a 3 to 3 amplitude, even though I've killed the 2 to 4.
May I ask you a question?
Yes.
So you are killing here the amplitude for on-shell particles, right? But actually, I mean, if you, I don't know, analytically continue the momenta, is it true that you should get the 3?
That fails. That's exactly
that fails. I
see. These pi epsilons.
I see.
That's in page 4 of the Torrielli review. Indeed, so the analytic by crossing one particle, we do mean continue to pi.
Okay.
Okay, so we now say that this theory has a chance of being integrable, so let's study as a classical field. Securing the knowledge that yes.
I've noticed that you started with pi to the 4th with wrong sign, but your course in the end has the right sign for all terms, right?
Oh, did I make it?
I was just wondering, is it normal that all of the truncations are consistent theories?
Wrong sign of which of the potential?
Oh, 5 to the 4 is blowing up downwards.
No. I thought it was so cos minus m squared. Let's see. Minus. Sorry. I should have said that. Then I need to also continue beta. I need to, because it's a cos. I need cos. Good point. Sorry. I should say something more. So let me erase this. I also need to do this.
You started with a theory that has a potential that doesn't have a minimum.
No. Maybe I made a mistake. So in my convention, minus. Sorry. Maybe I have to do this. Plus. It's this way because this is minus.
But why do you want it to be plus?
No, sorry. Let me write, so maybe I made a typo.
Maybe just a sign of landing.
Let me write the final So let me write the Sine-Gordon theory, and then let's see mistake. Sine-Gordon theory that I'm not fixed. No, but it has a plus. No. Yeah. So let's say after continuing beta to I beta, so from the cosh we go to the cos. Plus m squared beta squared cos beta phi minus 1.
Oh, sorry, I thought you wrote minus m squared.
Yeah, I probably put something, I probably made it up. Minus cos minus 1. Yeah, I might have made a typo.
Oh, it's a cos, not cosh?
Yeah, because I also need to continue to complex beta. Otherwise I get Cosh-Gordon, which is another theory. So in the end, I want to start from this level. I probably messed up some of the steps. I need to double check what the terms were. But this is the Lagrangian in the convention we normally write it.
Okay, but do you agree that the original theory has a potential for a lambda product?
Because
the potential
should be
goes down.
N minus v, yes. T, then T minus v.
Okay.
Yeah. So there must be a term. Okay, sorry, I'll go back and rectify this. But in the end, I want to study this particular theory, and this I can just take now and study the classical solutions. So let's study this classical solution. One thing that always happens, or tends to happen in classical integrability theory, is that the solutions are organized in very particular classes, and we often find solitons. So what is very characteristic of having an infinite number of conservation laws, which I'll show that this can be written in Lux air form, so we'll know it's classical integrable. But they have soliton solutions. Solitons are profiles which come from wave mechanics. A lot of these integrable equations were discovered in wave dynamics, and people found out that some of the profiles would preserve their shape, and even when you had two such solutions, although you don't have a superposition principle because it's a linear theory, they would satisfy some kind of superposition in some sense, and also they would preserve their identity as solitons. So all these features, which come about, for instance, in the KdV equation and other wave equations, are found in Sine-Gordon. So let's study the solutions. So Sine-Gordon solitons. So in order to obtain the solutions to the equation of solution, we require certain asymptotic conditions. Let's assume the following asymptotics. We have two types. One which we call soliton, and this is phi goes to 0 at minus infinity, now the classical field, so the profiles, and it goes to 2 pi over beta at plus infinity. 2 pi over beta, where again the cosine is 1. This 1, if you wish, is justified by it sets to 0 the vacuum energy, which will be the constant field equal to 0. But also 2 pi over beta has 0 energy, so it's another minimum. We'll draw the Sine-Gordon potential. It's called Sine-Gordon because the equation of motion will have a sign. And the potential looks like this. So it has multiple minima. And the first one is 2 pi. This is phi as a profile. Sorry, no, this is the potential. 1 minus cos, so it will be the negative of this bit. So this will be V of phi. So you see, the soliton interpolates between this minimum and this minimum. It goes here at 0, at x equal minus infinity, and it goes here, this is the field, at plus infinity. So it's a sort of tunneling solution. It's also called a kink, for reasons which will become clear once I actually write the solution. So there is an analytic solution. But let me first start and write the other one, which is the anti-solution, or anti-kink. This does this. It goes to 2 pi over beta at minus infinity, and it goes to 0 at plus infinity. It does the opposite tunneling. We'll be able to write it in a different way, so that it's more communicative. In fact, let me write the solutions, so that you can see that. And again, as an exercise, please feel free to check me that I got all the factors right. These are solutions to the equation of motion. The soliton, let me set n to 1 for simplicity. So the soliton phi is simply 4 over beta r time of e to the x minus a and the other one is with the minus. The soliton actually yes, so soliton and soliton 4 beta time e to the minus x minus. The soliton works like this. Visualize it, then it looks like a kink. So somewhere is A. A is called the center of the soliton. And this is 2 pi. The anti-soliton is the other way around. There is a relation there is a relation which shows that minus phi soliton is phi antisoliton minus 2 pi. Using the properties that we have found. In fact, phi, if I do minus, exactly, if I do minus this, it will be the same as this push down of 2 pi. This is important because it says, you see, the potential is even, the whole Lagrangian in fact is even, and so non-zero solutions must come in pairs. Lagrangian of Sine-Gordon is even under phi minus phi, and so non-zero solutions come in pairs, and indeed we see that basically the antisoliton is very simply related to minus the soliton. The pair is soliton-antisoliton. These solutions are characterized by some charge. So let me write this. So there is a topological charge. Where is this now? They tunnel through these first two vacua, we would say. So they carry a topological charge, soliton, antisoliton, carry a so-called topological charge. Q, it's a conserved quantity, beta over 2 pi, integral minus infinity infinity x. It's an integral of a local density, but the local density is a total derivative. So you might say is a trivial charge, because it just picks up the value at infinity, which for normalizable solutions it would be 0. But these are not normalized. They use the fact that the cosine is periodic, and so I can have finite energy. I invite you to check that the energy of these two solutions is finite, still with non-zero asymptotics, but this is just this height in units of beta over 2 pi. So it's plus minus 1 for soliton. Plus minus 1. It's phi of infinity minus phi minus infinity divided by factor, which makes it plus minus 1. If you wish, the conserved current, which is trivially conserved, is this. So I want to write it. J mu is some sort of epsilon mu d mu phi, which is conserved purely by commutativity of the partial derivatives. It's automatically conserved. And only because I'm on a strange asymptotics that I get the non-zero value. It's worth mentioning a geometric meaning of this. So, you see, because the potential is a cosine, there's some cos beta phi. Beta phi is basically an angle. So beta phi lives on an S1. And so beta phi represents a map. Beta phi is a map between R Minkowski, 1 plus 1, into a circle. And this map has winding. So effectively the angle has gone between 0 and 2 pi in the case of the soliton. So my map has wound the circle once. That's why I get plus 1. or minus 1. That's why it's called topological. Because it's basically a topological charge related to the winding. It's additive, I can do and undo, and it's conserved. So it's non-trivial. Once you put an amount, you've done a winding, and as you know, you can't undo it. You have to put another minus. Okay. This is one class of solution. It's not the whole story, because there are other solutions. Let me actually write another very important thing before I forget. So let me keep the drawing. Let me erase now the charge. I can give them some velocity. And this corresponds to the fact that these solitonic excitations are noticed to behave like particles, features of particles, so you can boost them. Boosted soliton. Let me just write. The boosted one has 4, and this is also a solution. R time plus minus for soliton antisoliton, n. Now I've reinstated n, so it's not n equal 1 anymore. I could have done it. It's just very difficult to keep it. Minus a minus d over square root of 1 minus b squared. This is a boosted soliton, antisoliton in some direction thing. So imagine this thing traveling be positive or negative.
Will there be an exponent inside there?
Yes, of course, yes, sorry. X. Yeah. Sorry. There are two notable features of this. One is the observation from, say, wave mechanics, that the profile moves rigid. You see, this is Galilean translation, just x minus vt. So the whole thing moves as a line. The second observation is that it behaves like a particle. There is a relativistic factor. In fact, I cannot boost it too much. V in modulus is less than 1. So it has features of a rigidly translated profile, Galilean, but it's also relativistic, because it remembers this particle value. Last two things I'm going to say is the final solution, which is notable, which is the breather. Then I'll give you the Lux pair, which closes the whole thing. And so let me write the breather solution.
There is a A to B theory would have a scar.
I'm not sure whether, again, it's a theorem. Most of the wave equations have solutes. If you see them coming from 2 plus 1 dimensional KP again, which is one of the other philosophies we were mentioning, that they all come from reductions of KP or self-Lorentzians. KP has solitons, and so in some sense they are kept. But again, there might be some very pathological theories which don't have. On the top of my head, I can't think of an integrable classical field theory which doesn't have some kind of soliton. And numerically, these things were shown to preserve their identity. When you scatter two solitons, they spend some time on top of one another and then recover their shape. That, you might recall, it's the same sort of as two particles only scattering, preserving their momentum. So there's a correspondence between soliton scattering and particles maintaining their identity and being effectively, there's so many conservation laws that the only way they can do is just exchange momentum and weight a bit on top of each other. But weight in time, quantum mechanically, is an S matrix. It's a phase delay of the wave function. So, any other question? Let's write the breather. The breather is, you see, these are effectively not eigenstate of the transformation phi into minus phi. And I cannot make eigenstate combination because the theory is nonlinear. So I don't have a superposition principle. Therefore, I'm just left with a pair of solid and non-solid. The breather is kind of eigenstate of that map. But in the following sense, let's first write it. The breather is this very complicated profile. Is 4 over b arc time root of 1 minus omega squared cos m omega t over omega cosh m square root 1 minus omega squared x. This can either be checked to be a solution or derived via the Gelfand-Levitin-Marchenko equation, which is a nightmare. But somehow it is a solution.
To be exposed again?
This time, unless I'm mistaken, no, probably this cosh might work as a surrogate of the exponent. Omega is 0, 1. So this breather oscillates on the spot. So it doesn't travel, but if I center it, it's a kind of lump. It goes to 0, so it's normalizable at plus minus infinity, and it oscillates up and down. That's why breather is. It breathes, it oscillates. And you see, it's not properly an eigenstate of the symmetry. Symmetry would be this. But minus phi is a breather that breathes in phase opposition. So it's basically the same solution shifted by some phase, which here I haven't put the phase plus phi, plus alpha. So it's kind of the same solution, but technically they're in pair. They come in pairs. There are various important facts about solitons, which I need. So this is just a solution. It turns out, in quantum, we'll find out with the quantum version, this is a bound state of a soliton and antisoliton. One feature that was discovered numerically is that solitons, so two solitons and also two antisolitons repel each other. Now, repel is a complicated thing to establish for wave profiles. You have to study the time delay they sit on top of each other. I've linked, again in the notes, to some website of a University of Oxford where some scientist has made simulations of these solitons coming. And in some sense you can see with naked eyes that they repel. You can give a meaning to the profile of repelling. But of course, one would have to have a complete numerical study and look at them dynamically. But for us, it's going to be fundamentally important because these objects will be fermions. In the quantum theory, they'll be fermions. They are profiles of the bosonic field, but they behave like fermions. So it will make sense that they'll be described in some dual theory by a fermion. The last thing I'll say is the Lux pair. So I need to be true to myself and show that this theory is integrable. And in those conventions, the Lux pair is this. I'll just write it very painfully. And one can check with Mathematica that the Lax equation satisfies, becomes coincident with the Sine-Gordon equation. So it's 2 by 2, and it's this I, beta phi dot, the time derivative, u. Let me just write L, and then for M, I'll refer to the notes, because we don't really learn anything at all, but it exists. Its beauty is that it exists. So let me just write L. And the fact that it's 2 by 2 is again mysterious. No one would have predicted. In fact, you see, the problem is that once I have found a 2 by 2 matrix that satisfies the Lax pair condition, I immediately found a 4 by 4, because I can put the L in block diagonal form, and it will reproduce Sine-Gordon in each block. I could find an 8 by 8. So there's not even uniqueness in the dimension, but I would say there's a uniqueness in the minimum dimension. The smallest dimension of the Lax pair, that seems to be defined. U to the minus beta. M is something similar. It's in the notes, and you can check that indeed, taking the derivative, you see it's linear derivative, so if you put it in the Lax equation, it produces second order derivative, and it all conspires, and it has this spectral parameter, which should generate infinitely many conserved quantities. Okay, let me stop here.
Intuitively, where does it come from?
I'm not sure there's any intuition except the fact that it will have to play the role of generating functions. So I could, in principle, if I have all the charges, in some models you can construct them step by step. For instance, if you look at the XXX spin change, which is another model, there's a way of constructing the charges step by step. Nearest neighbor, next to nearest neighbor, you could do it by hand, up to some extent. You could put them all in a Taylor series with a parameter u and generate a monotone. That's not the fastest way. The answer is, I don't know. When you write, I guess when you're playing with the equation and try to find the matrix, you notice that there's some freedom. And there's even a more bizarre case. There is a model, the Kepler equation, dynamical model, that's not a field theory. That works only because you have the spectral parameters. So the various equations are reproduced at different order in the spectral parameter. So it's not only the charges, but actually the equations, because it's a three-dimensional Kepler problem, so you get various equations at order u squared, u. So, but I'm not sure that there's any rationale. There are models where the spectral parameter dependence disappears, those are trivial, degenerate systems. The Lax pair is basically useless, doesn't give any information. But apart from that, it's again. There was a question.
Yeah, there was a question. I mean, here U is present at the level of L and M matrices, but not at the level of Sine-Gordon equation. So it disappears if I just brutally insert in the definition.
Yeah, you get, if you plug in this into the Lax equation, you get the Sine-Gordon. I forget whether it's overall multiplied by U, but equal to 0
I
Or
see.
it just, I forget actually, but it trivializes. It has no bear and so on.
So there is no coupling between phi and u. Okay.
Have you lost one path in
I should.
one of these points? In the lab?
Oh yeah.
So the matrix is permission apart from the I.
So the matrix would belong, I think it would belong to an Lie algebra, but ultimately it would be SU2, but this I, so maybe minus I, this would be SU2.
Yeah.
But yeah, this and this, sigma 3, traceless, there's a group which is this SU2.
So is spectral parameter unique for turbulent theory?
Sorry?
Is the spectral parameter unique for turbulent theory? Or is it another freedom by which I can...
Yeah, you have freedom, in fact. So you have freedom to reparameterize the spectral parameter. You have freedom to make a similarity transformation to these matrices, because the equation will only have commutators, so you can make similarities. You have the freedom of, as I was saying, stacking many of these in a chain. So there's a lot of freedom and ambiguity in the Lux sphere. And there's even a funnier case. There's a model where you have two Lux pairs of different dimensions. They both work just by accident, and they're not related. It's I found the references it's in these Laram notes that they're referred to. It's a strange model.
So is there any is there any equivalent? So like gauge fixing, is there a spectral parameter fixing theory on that?
I'm not sure. I think it's very reminiscent of fixing the gauge, going to the best Lux pair. I think there's an expert in the audience actually who might say whether there's a for every theory there's a favorite choice or things.
The one thing I would say is that Kevin's Masahita's ideas about some of these models, though not all of them, are that the spectral parameter is part of this mixed topological holomorphic Chern-Simons theory. So Chern-Simons theory is normally in 3D. This one is in 4D, which is weird. But it's not really 4D, it's more like 2 plus 2. 2 are the dimensions of the integrable model, and 2 are the complex spectral parameter Z, or U, that you have. And so in some cases it's possible that they can write down a Lax, where this Lax is really a holomorphic coordinate in these 4 dimensions of which this Chern-Simons theory lives. So the hope is that all the other models that they can't find are also going to be like this with some tweaking. That's an optimistic hope. Oh, sorry, I should say, sorry, yeah, that's a fair point. So, Kevin Costello and Masahito Yamazaki. Sorry.